Well, before focusing the attention to the content things, to content, well, without forgetting, please record that you attended. Well, in Metro class window, please find the attendance link and then record that you're ready in the classroom and attended. The password for today is tolerance. Using lowercase letters, please write this word tolerance. Tolerance and select present radio button. Click on save and then OK. Then see the things from my computer. Okay, then. In the content of last week, you found two video records. One of them said the record, it was the online meeting last week, talked about the dimensioning format, saying that extension line, dimension line, and lots of dimension rules. After finishing this part in the content, then, well, focus the attention to one more time the classification, functional dimensions, non-functional dimensions. And I said that, well, you're going to see what the meaning of this item in the classification reference dimension is studying on the CAT application. Well, this week in the content, you're going to find the video record. It is to educate you on the CAT part in AutoCAD in Inventor, how we show the dimensions. Answering this question, talk about the meaning of reference dimensions as well. But I think quite well know that functional dimension is the dimension of a functional feature, non-functional dimensions, non-functional features, dimensions of non-functional feature. And well, I think my example in the second video record, I use this assembly one more time, talking about the definition, saying functional feature, you mean what? In the example you see, it is an assembly, sub-assembly, and the age of this blue object is to reciprocate in contact with the surfaces of the channel. It is a feature in the design of the other component. So, well, to be able to have the clearance between the features of the components in the correct order, we need to determine the size of the features more precisely using smaller allowances, smaller tolerance. You know the definition. Tolerance means the difference between the upper limit and the lower limit of the size of a feature. It is called tolerance. Well, individually, designers individually considering the case, the clearance between the method features is to be in which order: very tight connection or very loose connection or medium order. Well, these are issued by the designer regarding the function of the object, okay, and also the expectations or demands of customer. In this example, the width of this channel, gray colored object, is functional. The age of this blue part is also functional. And well, in the same sub-assembly, we have one more functional feature. It is this cylinder. And of course, for the blue part, the whole of the object, you see this cylinder is to be mated into the hole. Okay. Well, if we arbitrarily size without considering the size of the hole, we arbitrarily size the cylinder, then when we attempt to mate it, assemble it, we may vanish. Or it may fit, but with a very great clearance, or undesirable great interference. So while designers should consider the relationship between this and that, and the clearance, order of the clearance, it is to be in which order, individually determine the tolerance for this golden part and the corresponding hole. These are functional features and their dimensions are functional. Remember, in the content of the last week, under the main title dimensioning, I deeply highlighted one more thing. I said that the dimensions shown on a technical drawing are just order of magnitudes. These cannot be exact values. Well, one of the reasons why they cannot be exact, for instance, 20 is not exactly 20. After the manufacturing stage, when the object is manufactured, if someone measures the distance from here to there, he or she may find the value not 20, less than 20 or greater than 20. But the important thing is that if the measured value is in the range bounded by upper and lower limits, those have been assigned for this feature, okay, then can say that this part of the object has been manufactured sufficiently correct in size. Cannot say exactly 20. One reason why nobody can insist on the exactness of the dimension, because even in today's technology, we have no measurement instrument to check not only the integer part, but also decimal places. We'll be able to say that it is exactly equal to 20. Well, start to speak in mathematically. Well, select another tool of Blackboard, the software, and then, well, this means 20. If you say, hocam, it is exactly equal to 20, then this means you mean the number is 20, okay, dot, it is to separate integer from the decimal part, and then well, at the decimal part you have all the digits, all the figures 0. How many figures, if they are all 0, can say that it is exactly equal to 20? Well, the answer to this question is infinite number of figures. Okay, at the decimal part, check whether all the figures, how many figures can be defined at the decimal part, infinite number of figures. Infinite number of figures, if all of them 0, 0, 0, 0, then someone can say that, okay, yeah, well, I measured the size of the feature and it is equal to 20. We cannot measure all the figures. We cannot measure the size of feature to check to see all the figures at the decimal part are all equal to 0. Why? Okay, because, well, turn back to the other sharing option and then bring the slides from another presentation from my lecture notes, okay, and then explain. Well, this short presentation is about measurement tools. Okay, today in industry these are commonly used. But in industry, you start using this measurement instrument in elementary school. I say in speaking informally, elementary school ruler, scale ruler. If you're going to use as the inspector, okay, at the field in the company, such a ruler, then be aware the resolution for an ordinary ruler, you see, between the telemarks, this is equal to 1 millimeter. That is the resolution for this instrument. Although in today's technology, for instance, on the technical drawing, we have a dimension and it is a functional dimension. It has been shown like this, for instance, 20. Okay, tolerance grade is H7. You know, in the format of today, we use IT tolerance grades. I hope you watched the second video record in the content of last week, and then you understand me if I say, when I say tolerance grade, IT grade, okay? Okay, well, in today's technology, when we convert such a number, such a dimension, then can find the upper limit. For instance, I'm not so sure for H7 it is equal to how much, but say that, example, assume it is in the order of that one, 20.0123, let's say. Yes, in today's applications, especially in automotive industry, aircraft industry, and pneumatic hydraulic systems, design of pneumatic hydraulic systems, it is true, we use 1, 2, 3, but some cases even more, 4, 5 significant figures at the decimal part. Okay, now, if the upper limit or lower limit, and also you know the definition, upper limit UL is equal to nominal value. Nominal value is the dimension it has been shown on the technical drawing. Okay, plus upper deviation. I said always write the expression this equality saying plus. If the deviation is negative, then it is going to be subtraction. Okay, from here deviation means upper limit minus nominal value. Okay. Lower limit, one more time, see the expression, nominal value, and V stands to say nominal value plus lower deviation, LD, lower deviation. Okay, well, you see here 20 is the nominal value, 20 minus, say that this is upper limit, for instance. Okay, this means upper deviation in my example is 0.0123. Okay, this is the upper deviation. Can write a similar number for the lower deviation, lower limit, lower deviation. Well, here, although we need to check whether the first figure at the decimal part 0, second figure 1, okay, third figure 2, etc. But if you by mistake use such a ruler, elementary school ruler, cannot see the decimal part, because using this ruler we can check the integer part only, whether it is 21 or 20. Cannot see these figures, cannot say anything about those figures, because the precision for this instrument, resolution of the ordinary ruler is 1 millimeter. In the market, how much money? Go to a stationery and then purchase it. Shopkeeper will say that, okay, 10 lira, 10 Turkish lira, maybe 20 Turkish lira. Okay, if it is manufacturing quality is higher, then maybe 50 Turkish lira. That is it. But today in industry, to be able to check whether the decimal part we have how many figures is equal to what, we use such an expensive measurement instrument. See the photograph, it is not a ruler actually, although by definition it's a measurement instrument, but it is a system. But in this photograph, what we have an object, it is an internal combustion engine block. Okay, well, allocating the probe of the instrument, okay, it's a transducer. If an inspection instrument is the one, it is input and output domains are different. Input is mechanical input, output is, say that, well, there is a display over here, can see the measured value in binary system, just decimal number. While within the box we have analog digital converter, or well, there may be a computer PC connected to this expensive instrument. Using the software can see the measured value. Output is electronical, input is mechanical. Okay, the irregularities over the surface of the object can be sensed by the probe. Okay, extension may push the probe. It is what? A mechanical effect, and that mechanical effect is converted to digital signal. And digital signal is displayed in the display of the instrument. Input mechanical, output electronical. So such an instrument is called transducer. In general, transducer. Extend the vocabulary. Transducer means it's an inspection, it's a measurement instrument. It is input and output domains are different. Okay, this is a transducer. Well, very expensive transducer. Elementary school ruler 10 liras. You can see the integer part only. This one is in the order of million Turkish liras. Very expensive. Okay, although you say you purchase such an expensive instrument to measure the size of the features of the object, paying in the order of 1 million Turkish lira, okay, it can indicate for any measured value at the decimal part 1, 2, 3, 4 figures. Okay, that is it. Not infinite number of figures. Well, in industry, we use today such a high precise, okay, expensive, very sophisticated design instruments. Very expensive instruments, but can say something only on the 10,000th of 1 millimeter. By the way, in this slide, well, this is just the photograph pasted from the catalog of a dealer of a company, German company, Turkish branch, published the document in Turkish. So the written things are in Turkish. But here, please pay attention to the temperature. Okay, the instrument is to be used, it is written in a room for inspection purpose. Room is to be kept at this temperature value. Yesterday, it was one of the questions, but which temperatures the dimensions are valid? The dimensions shown on a technical drawing are valid. The correct answer, 20 degrees Celsius. Okay, this manufacturers think that use this instrument at that standard temperature, 20 degrees Celsius. Okay, but can say only 1, 2, 3, 4. Very expensive one may indicate 5 figures. Okay, well, in our engineering laboratory, we have such an inspection system, but it is in miniature size. Can measure the size of very little objects only. It is in the order of 50,000 lira. Okay, 7 years ago, we paid 50,000 Turkish lira for this instrument. Okay. This instrument, saying, by the way, while you're taking MEC 114, you're going to see the details, is an inspection instrument. See, display is ready to indicate the measured value using decimal numbering system electronically. Well, the probe is over there. It can convert the mechanical impacts by the irregularities over the surface of an object to digital signals. This instrument is to measure not the size of the features, but the surface roughness of the object. Surface roughness measurement instrument. Again, sophisticated, expensive instrument. Well, these are dial gauges, okay? And using dial gauge, we can measure minimum distance 0.01 millimeter, okay? 0.01001 millimeter, not infinite number of figures. Well, this is very famous vernier caliper, in Turkish say kumpas. Okay, well, in this photograph, the vernier caliper is a transducer. You see it has a display where the measured value can be seen in decimal numbering system. Input say that there is an object, say we have a cylinder, and well, you see it is diameter is being measured. Input is analog, the mechanical output is digital. Vernier caliper. Using a vernier caliper, we can measure as the minimum 0.05 millimeters, 20th of 1 millimeter. That is it, 2 figures only. And if the second figure, for instance, say that dimension, upper limit of the dimension 20.03. No, since it is less than 5, it cannot be used. We cannot use this one. Okay? How much money vernier caliper? If it is manufacturing tolerance is, well, not so small, then you can purchase a vernier caliper in the market paying few hundred liras, maybe 500 liras. Manufacturing tolerance. By the way, for instance, on a technical drawing, there is a dimension. Well, today, I'm not so sure well, the time lapse whether it's gonna be sufficient to give some examples how can determine upper lower limits, okay, referring to the tolerance tables. If not, then well, using asynchronous technique, I'm going to record one more video. And watching that video, you can see how the upper lower limits can be determined. Say that for the dimensions shown on the technical drawing, yes, you determine that tolerance for the dimension for that dimension is equal to, for instance, A millimeters. Okay. If the tolerance of the feature for the feature is A millimeters, then the manufacturing tolerance of the inspection instrument, okay, it is also in a product. It has been manufactured. Okay, in the world there are few companies. Well, the most famous one is in Germany. The other company, as I know, in Japan. Okay, 2, 3, few companies manufacturing precise inspection instruments today in the world. But it is a product, so well, standard says the manufacturing tolerance of inspection instruments, especially for the mechanical parts, for instance, these legs are just made of metal, mechanical components. Manufacturing tolerance of the inspection system, okay, say that tolerance of inspection system, tolerance sub I, tolerance of inspection instrument should be maximum A divided by 10. In other words, the manufacturing tolerance of inspection instruments should be 10 times smaller the tolerance of the feature, okay, its size is to be measured. If the tolerance of this feature is A millimeters, then say that A divided by 10, find the tolerance, manufacturing tolerance for the inspection instrument, and in the market try to find a vernier caliper, for instance, its manufacturing tolerance is equal to that much maximum. Then that instrument can be used to measure the size of the feature. Well, this is sure that gonna be an exam question, latest in the final exam. Okay. This is, well, micrometer, another inspection instrument. Okay. As it is illustrated here, you see using a micrometer, the diameter of the cylinder is being measured. This is a transducer because it has a digital display, but this one is analog. Input, analog, output. Yes, looking at this scale part, vernier caliper, say vernier part, and then count the telemarks in alignment. Okay, while you're taking the laboratory courses next year, you're going to be educated on the inspection instruments, how they are used. This is an analog micrometer, and this one is a digital micrometer. What is the minimum distance can be measured using micrometer? 100th of 1 millimeter, 0.01. Yes, well, for vernier caliper, 0.05 is the minimum distance that can be sense measured. For micrometer, it is an expensive instrument in the order of few thousand lira. Minimum distance 0.01. Well, using such a very sophisticated inspection system, you can see minimum as the minimum distance 10,000th of 1 millimeter. Knowing all of such things, then, well, how you can say that, hocam, it is exactly equal to here 20. Okay, so nobody can measure the distance as exactly whether to check it is exact, because we have no such an instrument yet. The other reason, well, the size of any feature cannot be set precisely as equal to a certain specific value because, well, during the manufacturing stage, it is impossible to have the background noise, background oscillation, shaking effect in the building, in the structure. It will also shake the cutting tool as equal to 0, impossible. And also changing hardness of the material while the material is being processed via a plane cutting process. Since the hardness of the material is not uniform, cutting tool while the stock is being cut, cutting technology, well, accelerates or decelerates. Since the cutting tool will make accelerating and or decelerating displacements, well, cutting tool will deviate from the correct path, okay, and so where the size of the feature at the end of such a deviated cutting process will be cannot be exact, will be approximately correct, sufficiently correct, less than upper limit, greater than lower limit, or maximum equal to minimum equal. So as I said in the second video record, one more time saying, for each dimension, we need to inform the technicians, waiters on the upper lower limits. In this, well, for functional dimensions, we use IT tolerance grades today. For non-functional dimensions, well, tolerance class definition. At the title block, within the box, it is to be entitled writing this phrase general tolerance, while using standard letters, lowercase letters for the size tolerance, capital letters for geometrical tolerances. Geometrical tolerance, repeat again, saying, by the way, just deeply studied in MEC 114. Okay, mechanical engineering students are deeply educated on not only size tolerance but geometrical tolerances. Saying geometrical tolerance, we mean, in short, the allowance, okay, to control the form of the features, flatness of feature, perpendicularity of feature, parallelism, runout, circularity, cylindricity, etc. Are geometrical characteristics, okay, and to control the form of the features, we use geometrical tolerance technique. It is subjected in MEC 114. In this course, you're responsible from the associated things on size tolerances, where the lowercase letter in this example stands to say tolerance class is force. Okay, this week I'm going to clarify what does it mean tolerance class. So for non-functional dimensions, this address is the correct address to refer at the beginning, and then see the tolerance class letter and then deal with the rest. Refer to the correct table and determine upper lower limit. Okay, and then refocus the attention to one more time the format. Beforehand, showing the functional dimensions, we use this format: nominal value, next to nominal value, deviations, upper lower deviations. Unit of the dimension, nominal value, and the unit of deviations are the same. This is in millimeter, this is in millimeters, so it can be directly processed. But in today's format, instead of writing the deviations directly, we write tolerance rate. It is a code, so this code is to be converted to upper lower limits. If your technicians, as I said, remembers last week in my delivery in the second report, not so educated technicians, then on behalf of those staff, make the necessary evaluation and determine upper lower limits or upper lower deviations. 30F7 corresponds to this deviation, that deviation. If you this plus that, say, can find upper lower limits. Showing the functional dimensions next to the tolerance rate, writing the upper lower limits is a good practice. And one more thing you should learn or have to learn is the tolerance rate letter. If the dimension is the size of a muscular feature, feature, then we use lowercase letters. If the feature is a feminine feature, formally speaking, say empty space, there is a channel, there is a hole, and the dimension is the size of such a feature, then we use capital letter. Writing tolerance rate, we use capital letter. Example, for a hole, the dimension has been shown like this: 45 C H8. H8 is the tolerance rate, and it is in uppercase. Shaft is a muscular feature, as an example. You see it is tolerance rate in this example has been shown using lowercase letters. Okay, and then, well, functional feature means it is the feature it is to fit in or onto another feature. Okay, so okay, well, open the other presentation quickly. It is not already open. Dimension chapter, and yes. Okay, then, well, time to talk about the types of fittings. If one entity is to find its place into or onto of another entity with another entity, then we say that it is functional, you know this. But if the entity going to be in a fluid, in contact with a fluid, for instance, atmospheric air or a liquid, then say that it is non-functional. But if it is going to be in contact with a solid feature, the solid feature of another object, okay, object is an assembly, and in the assembly there are more than one component. So one component is to be assembled with the other component. And at the assembly, well, some of the features will be in contact with the features of the other component. So, well, start talking about, in such a case, clearance order of clearance. Well, this slide under this title, size tolerance, just to inform you on the say the types of the fittings. If one entity is to find its place into or onto another entity, we say that fitting. There is a fitting. It is to fit. In this graphical illustration, we'll say that this is a muscular feature, and this muscular feature is to be fit into this empty space. Well, this space is feminine feature. Okay. If the type of fitting, yes, in the diagram we use special phrases to amplify the order of clearance. If it is clearance fit, then this means in all the cases, no matter this feature is in upper limit or lower limit, that feature in upper limit or lower limit, when they are manufactured and mated, then there will be always between them a clearance. Of course, if the masculine feature is in minimum size, feminine feature is in maximum size, then the clearance will be maximum order, in maximum order. Opposite case, minimum order. Minimum or maximum clearance, but in clearance fit, sure, always there will be a clearance. When we make the components, then always can find that still there is an empty space between the surface of the objects. But if it is fitting type is interference fit, in English we say interference fit, well, cannot find clearance between the surface of the objects. Not clearance, but very tight connection, interference. Although there's an interference, the size of muscular feature, this is the muscular feature, greater than the size of feminine feature. How it is mated, how it is assembled. Well, the common practice in industry is that put the feminine feature into a furnace. There is a furnace, treatment furnace. In the furnace, heat it up. You know, second video record or first video record in the content of last week, I already told you about. To remind you on the thermal expansion phenomenon. If the object made of crystallographic material, okay, when its energy level is increased, it expands. Okay, to be able to make the size of feminine feature in the order of muscular feature, even to have a clearance, put the feminine feature into object, it has a feminine feature, into a furnace. Okay, at a higher energy level, it is size going to be in the order of the size of the muscular feature, because it will expand. Well, this muscular feature, let's say, is in the order of 20 degrees Celsius. This is in the order of 200 degrees Celsius. So, well, at such a high energy level, the size of the empty space is sufficiently large to be able to assemble the muscular feature. Okay, at such an energy level, well, without any difficulty, can assemble the muscular feature, and then, of course, while this hot body turn back to its equilibrium state with the others. So, well, when it turns back to the the steady state, then between this and that will be interference. Very tight connection. Depending on the tightness, well, the interference may be minimum or maximum order. But in all the cases, this has been manufactured in upper limit, the other one lower limit, or any other in the range. There will be an interference always. Yes, interference fit, sıkı geçme in Turkish. While the others are just intermediate fitting types, line fit means, well, when the components are manufactured and assembled, we may have by chance no clearance, zero clearance, or a clearance, but not interference. It is called line fit. Transition fit, well, by chance, when they are manufactured and mated, may have a clearance or an interference. Who knows? 50-50 chance. Okay, there may be a clearance between the components or maybe an interference. Okay. Now, knowing these definitions, I know this is the expected question in the mind to find and ask the teacher. Hocam, how we can guarantee to have the fitting as clearance fit or interference fit or line fit or transition fit? The answer of the question is that on the technical drawing for muscular part, okay, well, after individually selecting the tolerance grade, why are showing the tolerance grade on the technical drawing for this? Why are showing the specifically individually selected tolerance grade on the technical drawing of the other can guarantee to have the fitting in the correct order. At this point, I'm going to give an example, but before the example, first address this table. Yes, this is a very valuable table. You can find the recommended IT grades. Okay, to have clearance fit, transition fit, or interference fit. For each main group, we have further classifications. For instance, loose running fit, free running fit, close running fit, and sliding fit. These are under this group, under clearance fit title. Well, if in the jargon we say loose running fit, if the fitting is loose running fit, then the clearance order will be highest. Okay, if it is sliding fit, clearance order will be minimal, very small. Similarly, interference fit, location interference fit, we use this phrase as the type of the fitting, locational interference fit. Okay, then this means interference is not so much. But if it has been said, say, force fit, this means fitting is in the highest order, say, interference is in the highest order. If it is location interference fit, even you may insert the muscular feature toward the hole, into the hole in your hand. Okay, your muscular force may be sufficient to push it, okay, to make it. But if it is force fit, no. With your muscular force, the force can apply with your hand won't be sufficient. Using press machine, applying very great pushing force can make one component into the other one. Okay? So, well, this is important. Depending on the type of the mating, okay, designer fix whether function of the object, considering the function of the object and the expectations and or demands of customer, designer select the fitting type. For instance, designer selected free running fit. If it is free running fit, then from this table, this part of the table, see, under whole basis column, along the whole basis column, H8, F7. These are the recommended tolerance grade. I'll clear the slide and then do it again. Free running fit, for instance, or close running fit. If the selected fitting type by the designer is close running fit, then this is on the technical drawing of the object component, it has a feminine feature, and that feminine feature is to be mated with the feature of the other component. Okay, tolerance grade is to be H8, and showing the dimension of the muscular feature on the technical drawing of the other component, F7 is to be used as the tolerance grade. Okay, if the components are manufactured using this tolerance and the other tolerance, then yes, when they are assembled, then ensure that while the type of fitting will be close running fit. Well, in my example, in Inventor using this solid model, I said that, well, the channel size is functional, the age of this blue part is functional. Okay then. On the assembly drawing, yes, this is the assembly drawing file. On the page, what we have: front view, top view, left side view of the assembly, and it's an assembly drawing. Well, it is in the format exist. Well, the ID balloons are used to indicate the components. First component, second component, third component. Okay, and at the parts list, at the say the just above the title block, we have such a table, and in the table, the components to their ID numbers are listed, their names are written, and some other technical notes are written at the parts list. In civil engineering convention, there is no ballooning, there is no parts list. Civil engineers or architects just indicate the component, and writing a technical note say that it is, for instance, brick wall, it is door, it is gypsum layer, etc. Okay, in civil engineering, and also in mechanical engineering applications, aircraft, aerospace engineering applications, chemical engineering applications, the size of the dimensions, the size of the feature may be needed to control in the order of thousandth of 1 millimeter, 100 times of 1 millimeter, 100th of 1 millimeter, thousandth of 1 millimeter, 10,000th of 1 millimeter. But in civil engineering, the tolerance is very high. In engineering, mechanical engineering, the tolerance may be in the order of, in automotive engineering, aerospace engineering, pneumatic hydraulic system design, while the tolerance may be in the order of 10,000th of 1 millimeter, 0.00, etc. But civil engineering tolerance, order of tolerance is just even centimeters, yeah? Because when the door is attempt to fit into the door opening in the structure of a wall, well, cannot find the size of the door opening in the order of the door, size of the door, then, well, it is not a difficult thing to furtherly cut the wall to increase the wall opening, say, door opening of the wall. If when we assemble the door, when we fit the door into the door opening or window opening, can have very great empty space between them, then using a bulk of cement, concrete, or just injecting some foams, special chemicals, can easily fill in the blank, fill in the space. So in civil engineering applications, architectural applications, show the nominal values, we do not think about tolerance, because the tolerance is in the order of few centimeters, not thousandth of 1 millimeter, but few centimeters. In civil engineering, tolerance, this part of the course content is not so important. Civil engineering, well, just know the dimension format and be able to show the dimensions correctly. Not focus the attention to the upper limit, lower limit. But in the other branch of engineering, well, the upper and lower limits are quite important. And then in this example, well, see the technical drawing, detailed drawing, let's say not completed because quadrant symbol has not been shown. Okay, name of company not written, dimensions not shown. So cannot say that this is just a detailed drawing. Not yet. We have the views only and one of the dimensions. But because my purpose is to focus the attention to our method, how we can guarantee to have the fitting in the correct order, clearance fit or interference fit, etc. Well, you see the dimension for the edge of the blue part. You see the edge of blue part is a functional feature. So it is dimension. Here it is, a functional dimension. Well, F7 is the selected tolerance grade. How it is selected? Well, refocus the attention to this. Close running fit. You see here, the selected fitting type is close running fit. If it is close running fit, then the muscular entity is to be sized using F7 as the tolerance grade. And feminine is H8. At this point, it is important. Your learning outcome. You learn that capital letters are used in writing or showing the IT tolerance grades for feminine features. Lowercase letters are used in writing or showing the tolerance grades for muscular features. Thanks to such a learning outcome, can take the recommended IT grades and then use them correctly. H8 is the tolerance grade for having close running fit, tolerance grade for feminine features. Okay, and then see, this is the technical drawing. On the technical drawing, it is to inform the reader on the shape and size of the blue colored component, the size dimension of the functional feature F7, and this is the technical drawing of the part or the component. Yes, this one. Yes, the gray colored one. This one. Technical drawing. Where it is? Yes, here it is. You see, the dimension here, it has been shown on the left side view, is to inform the reader, technicians, on the size of the channel. Channel, width of the channel, depth of the channel is 5 millimeters. Pay attention, please. 5 is the nominal value. Showing the dimension of the channel on the technical drawing of this component, write the same nominal value. But next to the nominal value, individually selected IT grade. It is the recommended tolerance grade for this type of fitting. Which one? Close running fit. Okay, on the technical drawing for the blue colored component, yes, 5 is the nominal value. Nominal values are the same. 5 millimeters here, 5 millimeters there. But the tolerance grades are not the same. Here for the feminine feature, tolerance grade is H8. For the muscular feature, tolerance grade is F7. Yes, of course, the rest is the issue of technicians. Technicians, operators, applying the cutting process, okay, need to set the size of this part in the range, well, it corresponds to the F7, this tolerance grade. After manufacturing, when we measure the thickness of this part, if we see that the measured thickness is less than the upper limit, maximum equal, or greater than the lower limit, it corresponds to F7, or minimum equal to, then can say that it is okay. It has been manufactured as sufficiently correct in size. I can say similar things for this channel. After the manufacturing, of course, quality control engineers measure the size, the depth of the channel, whether the measured size is in the range bounded by upper and lower limits. Those correspond to the H8, 5H8. Okay, yes, this is our method, yeah, dear students. In industry, yes, individually selecting tolerance grades, we granted to have the mating in the correct order, clearance speed, etc. Okay, and then Well, to see the other things, refocus the attention to the slides of my presentation. Yes, this table is really very valuable table, and latest in the final exam, you're going to use this table, okay, to determine the tolerance grades. Okay. And then this slide, yes, well, Hall bases, shaft bases. What does it mean, Hall bases? There is an illustration here. In Hall bases, it's a method actually during the manufacturing, okay, to be able to, while trying to set the size of the masculine and feminine features, these are to be mated, to be assembled. In Hall bases, we do not change the size of feminine feature. Well, if the muscular feature is not in the correct size, its diameter is greater, although we need to have clearance fit between the surfaces, there should be clearance, but the stock size is greater than the size of feminine feature, then cut the material, okay, decrease the size of muscular feature. Yes, we do not change the size of feminine feature. We change the size of by cutting the muscular feature. Decrease diameter, decrease diameter. If it is in this order, interference fit. If you decrease the diameter, cutting the material, applying turning process, for instance. If it is a cylinder, turning process. If it is a right prismatic object, then the material is to be removed from a surface for having a flat surface in the correct size in the end. Then using a crank shaper or a milling machine, a planing machine, planing process, can cut the material, and then have, for instance, slide fit. If you need to have clearance fit, then cut the material further and have the clearance fit. This is very practical because, well, we can adjust the milling machine or turning machine very precisely, and then can set the size of the muscular feature without any difficulty to the correct order. But in shaft bases, the method is different. In shaft bases, to be able to have the clearance between the muscular and feminine feature, we change the size of feminine feature. Especially if the feminine feature is a hole, then, well, in the market, may not find a proper cutting tool to increase the diameter of the hole. Because in industry, we have standard, say, cutting tools in size, well, say that you need to have the mating in a certain specific order. So for having the mating in that order, say that the diameter of the drill is to be, for instance, 12 point, let's say 5.3. Okay, well, go to market and try to find a drill cutter, cutting tool. Its diameter is equal to that much. Sorry, you cannot find it. What can you do? So it is the main reason why shaft bases is not recommended as the technique to set the size of features for having a fitting in the correct order. Because in the market, drill cutters are in standard order and cannot find any other to set the size of feminine feature. But in Hall bases, since using turning machine or milling machine or crank shaper can set the size of muscular feature much more easily, no need to use drill cutter, cutting tool, hole drill cutter, of course, then, well, we can more precisely decrease the size of muscular feature and then achieve to have the mating in direct order. So Hall bases, unless otherwise mentioned, is the recommended technique. So in this regard, well, I say that, don't forget, latest in the exam, well, make the recommended tolerance grade selection from this column. Okay, although in this table we have shaft bases column, seldomly we make the selection from shared basis, because shared basis technique is impractical to apply to use. Make the grade selections, tolerance grade selections from all bases column. Okay, don't forget. And then one more thing, IT grade. In today's format, showing the dimension of a certain feature, for instance, on the technical drawing, this is the dimension, okay, for a muscular feature. For instance, the size is 30, okay, let's say G. G is the grade letter. How about the grade number? IT grade numbers are along the spectrum. Okay, select the proper IT grade number, for instance 7, and write it after the letter G7, for instance. Okay, IT grade numbers are in the spectrum, and in the format, IT grade number is preceded with a letter, and both of them as a whole is called IT grade. This is the grade number, and that is the grade letter. In the spectrum, well, actually, the spectrum has two more grade numbers, 17, it continues, 17, 18, okay, two more grade numbers. Normally in machine industry, automotive engineering, design of pneumatic systems, hydraulic systems, aircraft industry, we make the selection from this part of the spectrum. While the IT grade corresponds to tolerance values. The deviations increases in this direction. The minimum deviation for a certain nominal value, okay, comes from this IT. If IT grade number is 0,1, then this deviation is very small, smallest. Well, since standard says that the manufacturing inspection instruments should be 10 times smaller than the tolerance of the features to measure, well, and since the deviation increases in this direction or oppositely decreases in the opposite direction, as it is written in the design and manufacturing of measurement instruments, we make the IT grade selection from this part of the spectrum. Go to market and ask the shopkeeper to purchase a vernier caliper. If you say that IT grade for that vernier caliper is 5, then shopkeeper will say, okay, sir, pay, for instance, 600 lira. If the manufacturing tolerance grade for the inspection instrument is 5, 6 or 5, then it may be 600 lira. But if you say that, yeah, it is IT grade is 1, then shopkeeper will say that, okay, sir, if you pay, for instance, 2,000 lira or 3,000 lira, you can purchase. But if you say that IT grade, manufacturing tolerance grade, or the inspection instrument is 0,1, then keeper may say that if you pay 10,000 lira, 20,000 lira, okay, you can purchase. Okay, while this part of the spectrum corresponds to the IT grades, these are used for sizing the inspection instruments. For non-functional features, well, the IT grade corresponds to this part of the spectrum, 16, 17, 18. Those IT grades corresponds to the very coarse tolerance classes. Talking about the things to do, how the upper lower limits and thereafter the tolerance of functional dimensions are determined, I'm going to explain a little bit in detail. Okay, these are the IT grade numbers. IT comes from this phrase, International Tolerance Grade System. IT. We generate this abbreviation from this phrase. Okay, according to ISO definition, it is the grading system. Okay, this table is to answer the question, which process as the finishing last process is applied, okay, for setting the size such a manner that the IT grade corresponds to 6, 7, 8, etc. Well, for instance, if IT grade is 6, dimension on the technical drawing has been shown, for instance, blah 50 millimeters, okay, and then IT grade, for instance, H6. If the dimension has been shown with this IT grade H6, 6 is the grade number, then see from this column, applying which manufacturing processes as the finishing process can have IT grade as 6. Well, cylinder, if the surface cylinder, yes, applying grinding process. Since you see the black bar, just match to this IT grades. Applying the grinding process. Yeah, well, Ahmed, it is too late to record that you attended. It is almost the end of the session. Well, I am going
Hocam,
to write the password to record that you attended at the beginning to 15 minutes.
Hocam, I
But,
just came from Lefke because there was the fire in campus and I had
okay,
to go to
then,
Lefke. So,
yes, I know the trouble for me. But say technically impossible, cannot record that you attended. Please send an email message about your excuse, and then on behalf of you manually, I can add that you attended. Okay?
okay, Hocam.
After the class meeting, send a mail message
Okay,
explaining your situation. Okay,
okay, Hocam.
continue, dear students. Well, Ahmed, please mute your microphone. Thank you. Okay. Well, this means applying the grinding process can set the size of this feature. Okay, IT grade may be 6. But if you select milling process, for instance, then you see for milling process, IT grade cannot be 6. It is going to be wrong process. Finishing process cannot be milling process. Drilling process. Applying drilling process from here can see that the IT tolerance rate may be 10, minimum, maximum 11 or more. So this is also a valuable table to answer such a question. Okay, then applying which process as the finishing, finalizing process can set the size of a feature, for instance, as 50H6, 50G7, 50R10, etc. Referring to such a table, can select the correct or proper finishing process. Of course, second year taking the manufacturing technologies course can clearly understand that, for instance, if you say that turning process, turning process is the wrong process to apply for shaping a flat surface. If the surface is a flat surface, do not apply turning process, but apply milling process. Okay? Or planing process. Planing, milling processes are the process, okay, to cut material for creating and via which creating flat surface and via which setting its size. Which process is to apply, okay, as the finishing process for which feature? Well, to answer the question, first you should know which process is the correct process to apply, and also you must consider the tolerance grade. Okay, if tolerance grade is 5, although it is so, you selected, for instance, milling process, then this means you made a mistake, because applying milling process, IT grade cannot be 6, cannot be 5. minimum can be, you see, 10. Okay. These are really important details in engineering. Well, this slide is about Turkish vocabulary. In English, we say free running fit, close running fit, sliding fit, etc., etc. In Turkish, our technicians say that hareketli geçme, preste geçme, çakma geçme, kalkma geçme, etc. If you're interested, you can refer to this slide. And then, well, in whole basis, these are recommended pairs. Capital letter, the one written with capital letter is the tolerance grade, recommended tolerance grade for the feminine feature. The tolerance grade written with lower letter is the recommended tolerance grade for the muscular feature. Yes, today's format, and you know, writing the corresponding upper and lower limits today is good practice, especially your technicians are not so good in converting the code to a certain, say, upper lower limit for the communities of them show. Okay, and then now, this is a very important slide. Okay, we have a technical drawing, say that, okay, this is lighter in tone. Say that on the technical drawing, we need to show the dimension of a feature. Okay, this is the dimension line, etc. And then size, for instance, say that 50. And then the rest. Well, metric tolerancing means in accordance with ISO. Okay? Well, the question is that one. Writing the nominal values, well, in the case whether we need to write the integer part of the size or together with it is decimal portion, decimal place. That is the question. Whether the nominal dimension is to be written as an integer or after putting a dot, well, show the significant figures, show the figures at the decimal part. That is the question. And ISO says that, ISO, International Organization, says that if deviation, this dimension, for instance here, example, plus minus in the old format, deviation values. Upper deviation, you see upper deviation in this example, UD means upper deviation, is plus 0.1. Lower deviation is equal to minus 0.1. Well, if deviation, you see deviation starts from tenths. You know, well, the decimal places, talking about decimal places, say that this is the decimal place marker. In engineering, we use dot. Okay, figure, first figure, second figure, third figure, etc. Well, this is the tenths. This is the hundreds. This is the thousands. This is the place to write the 10,000s. Onda birler basamağı in Turkish, yüzde birler basamağı, binde birler, 10.000'de birler. ISO says that if deviation starts from the tenths, then show the nominal value as integer. Example, you see 0.1, 0.1. Deviation just starts from tenths. So writing the nominal value, show it as integer. Okay? But if deviation starts from hundreds, in this example, you see deviation. Well, this is space holder 0. It is a figure, but you see a significant figure starts from the hundreds. Okay? Well, since the tenths is just a space holder, okay, it is 0. The significant figure starts from hundreds. Since the deviation starts from hundreds, then according to ISO, the nominal value must be shown with one figure at this decimal part. Okay, if it is the case, say that in our example, the deviation is equal to 0.04. Since deviation starts from hundreds, then show this dimension with one figure at its decimal part. What is the value of the figure? Well, in this example, let's say 1. Show the nominal value like this. And then the rest, write the tolerance curve. For instance, it is H7. Okay? Don't forget, in determining whether the nominal value is to be written as integer or decimal number, okay, first refer to tolerance table and find the upper lower deviations. If both of or one of them starts from tenths, then show the nominal value as integer. Do not show any decimal part. But if deviation starts from hundreds, one of them at least, then show the nominal value well, as a decimal number with one figure at its decimal part. Show the tenths. If the deviation, for instance, starts from thousands, say that you found the upper deviation or lower deviation, referring to tolerance table. How I'm going to answer this question probably next video record. Okay, refer to table and then you found the deviations 0.06006. Since the deviation starts from thousands, binde birler basamağı, then show in that case the nominal value as 50.1, and then what is the value at the hundredths place? For instance, it is, let's say, 3. Okay, show the nominal value like this with two figures at its decimal part, and then the rest say that, for instance, H6. Okay, I hope it is clear. Well, integer or decimal, nominal value is to be shown as integer or as a decimal number. The answer comes from the value of deviation. If deviation starts from tenths, show the nominal value as integer. If deviation starts from hundreds, show the nominal value as a decimal number with one figure. If the deviation starts from thousands, then show the nominal value with two figures at its decimal part. This is the ISO rule. Inch tolerance in following slide means ANSI rule. American Society Standardization Institute says that it is opposite. Well, if the deviation starts from thousands, for instance, this is the deviation, then writing the nominal value, what is the nominal value? For instance, 30. Do not say 30, 30 dot, and then use 1, 2, 3 figures at the decimal part. How many figures do we have? The deviation has how many figures? In this example, 1, 2, 3 figures. Since deviation has 3 figures, then write the nominal value with 1, 2, 3 figures. Okay? Showing the dimension, write 1, 2, 3 figures. The number of figures at the decimal part of nominal value and the number of figures of the deviation should be equal. This is American format. Okay? 3 figures, deviation, 3 figures, nominal value. Nominal value, say that 50. 50 dot, 1, 2 figures. This is American format. But ISO format is completely different. Well, you see deviation has 1, 2 figures, but nominal value has 1 figure only. The measure is different. Repeat again. If deviation starts from tenths, show the number, nominal value as integer. If it starts from hundreds, well, write the nominal value as integer. It's a decimal number with 1 figure, and so on. Okay, keep in mind, study this part of the content one more time at home. I strongly recommend. And then now, time to give an example. Okay. In the example, let me use this empty space. Say that on the technical drawing, we have a dimension. It has been shown in the format of today. For instance, say that 30 H7 is the dimension. Sure, later in the final exam, I'm going to ask you on such requirements. Determine the upper limit, lower limit, and the tolerance for this dimension. How? For functional dimensions, in my lecture notes, can find not the table entirely, but the selected portion only. Here it is the table. Okay, in whole basis, okay, this table has been prepared, and say in the document published by standardization associations, these are provided. But first, introduce you to the structure of this table. Repeat again, this is the table, okay, in this course to refer, and of course, in real life, in industry as well, for functional dimensions. Well, at the top, we have a row. Along the row, we have the titles of the columns. You see the titles use the IT grades. Okay, for this column, IT grade is H9, and that is the corresponding column, H9 column. This is H7 column. Okay, this is G6 column, etc. And F7 column. Okay. Of course, well, we have lots of IT grades, but here this is just for school purpose. Only can see the selected ones finally. Okay, the table actually is a very large table. This is one of the pages of the table. IT grades at the top, and for each IT grade corresponding to the column. Okay, this part of the table, we have two columns. Okay, over 2. Well, these are the ranges to locate the nominal value. What I mean? Well, I forgot the dimension, but write it one more time here. Say that this is our case in the example. We have a functional dimension. It is 30. It has been shown as 30 F7. F7 is the IT grade. Okay. And our purpose is to determine upper limit, lower limit, and the tolerance for this dimension. Well, the first thing to do is that in using such a table, 30, nominal value is 30. Locate that number in the range. Well, here, this part of the table, we have range. For instance, if the nominal value is 6 or greater than 6, 10 or less than 10, then this means the correct range to select is this one. But not only in this table, for all the other tables, unless otherwise mentioned, it is a rule. If there is a range in the structure of the table, the first number of the range is not included. Second number is included. Well, for instance, here our nominal value is 30. See, 30 is the boundary value for this range, boundary value for the following range. 30 is just the threshold value. Well, this is the question in selecting the row via locating the nominal dimension, nominal value of the dimension in the range, whether you're going to select this range or the other range. Nominal value is 30, 30, 30. Well, the general rule says that first number is not included. So since 30 is not included in the range, can say that if the nominal value is greater than 30, okay, then it's this range. But if the nominal value is equal to 30 or less than, then this is the correct range. Since 30 is included to this range, well, need to select this range. Okay, well, for this dimension, the correct range is this one, not the next. Be careful. First number of the ranges are not included to the range. Second number included. So while this range is the range of the numbers, these are greater than 30, say greater than 80, less than or equal to 30. Yes, since our nominal value is equal to 30, then this is the correct range. After selecting the range, then to find the deviation value, yes, in this table, this main part of the table, now I bounded the main part, what we have the deviation values. Within the pigeon boxes, we have upper and lower deviations. These are all deviations. Okay, to be able to find the deviation for 30F7, follow this row. Okay, first we concluded that 30 is the nominal value. It finds its place within this range. So start to follow this path. Okay, to where? Well, you know, IT grade is F7. F7 column is this column. Follow this column. And then to this meeting box. Within this box, yes, following the IT grade column and the range row, we found this pigeon box. And in the pigeon box, what we have? Deviation values. Okay? Both of them negative. Okay? For this IT grade. But here, there is extremely important detail to pay attention. In the design of this table, all the deviation values are in micrometer. The unit of measurement is micrometer. Don't forget this. Unit of measurement for the deviation values, these are all shown within such pigeon boxes, is not millimeter, micrometer. So as it is highlighted at the top, just under the IT grade row, to be able to process those numbers via adding or subtracting with the nominal value, first we must divide them by 1,000 to be able to convert the number which is in micrometer to millimeter. Okay, so continue. Well, from here, see that upper deviation is minus 20. Okay, write that upper deviation. Upper deviation, first write the deviation. Upper deviation is equal to minus 20. Don't forget to write unit of measurement. It is to inform me and also notice yourself that it is not millimeter. Micro from Greek alphabet. Okay, don't forget to use a long tail. Otherwise, short tail. If you're writing micro, if you use short tail, it will look like millimeter. Do not use short tail. Exaggerate the case and a very long tail. Micro from Greek alphabet. Okay, and lowercase m, micrometer. And then convert to millimeter. Okay, by dividing it to 1,000. Minus 20 divided by 1,000. Now say upper deviation, sorry, minus 0.002. I'm true, I think. Yes, 1, 2, 3. Yes, 0.02 millimeter. This is in millimeter. Okay, how about lower deviation? Upper deviation is equal to minus 0.02. lower deviation is equal to minus 41 micrometer. Okay, divided by 1000, it is equal to minus 0.041. How many figures we have? At the decimal part, 1, 2, 3. So add one more zero here, 1, 2, 3 figures. These are the deviation values, and then continue. Now, upper limit is equal to upper deviation plus nominal value. Nominal value in our example 30, okay, plus deviation value minus 0.020. Lower limit is equal to 30 plus, in the parentheses, minus. If it is negative, then it is going to be subtraction, 0.041 millimeters. Okay, calculate and then write. Here, showing the dimension, the deviation value with such a figure, we highlight that the precision resolution in sizing this feature is in the order of tens, hundreds, thousands. Okay, in elementary school, math teacher said that, yeah, are you stupid? Why are you writing the zero? In engineering, it is extremely important to highlight the precision. It must be shown. Okay, if you want, I can use a pocket calculator. Okay. Actually, I forgot the number, but try to 30 set minus 0.41. Sorry, corrected. 30 minus 0.041. You see the lower limit 29.959. Okay, 29.959. See the value, yeah, tens, hundreds, thousands. That is the lower limit. What about the upper limit? 30 minus 0.0, well, the number I forgot. Yes, 0, 2. Okay. Yes, 29.980 is the upper limit. Okay, that is it. For functional dimensions, this is the thing to do for determining upper lower limits, my dear students. I think the example, given example, became clear enough to answer the question. Knowing the IT grade, how we can determine upper lower limits for functional dimensions. How about non-functional dimensions? Example, for instance, in this example, for which one? 60. For instance, 60. 60, the height of the object. You see, next to this number, we have no IT grade. This means it is non-functional. For non-functional dimension, in the example, refer to the title block. And in the example, the first is the size tolerance class, lowercase c. Okay? First, see from such a box the class letter. It is C. And then, how about the rest? Refer to the table. Those are provided by the Standardization Association. Well, the international standard ISO. Yes. ISO in the publication code is 2768. Actually, at the title block, the written code is this number. Publication date is 1989. Well, this part is about the upper, lower deviations and corresponding limits for non-functional dimensions. At the explanation, it is written, you see, if the dimension is the one, it has no individually determined and shown tolerance grade, then yes, this is the correct document to refer. For non-functional dimensions, refer to the first part of the publication. Why? To find such valuable tables. Okay, for linear dimensions, in our example, say that the left side with the height, I said that for the height of the object, it is a linear distance and the nominal value is 60. Okay, it's a linear distance. Thickness, well, height, depth, width, diameter, these are all linear dimensions. For linear dimensions, the table to refer is the first table. Okay, and these are the class letters. Well, the class letter is gathered from the title block. In our example, class letter, tolerance class letter, tolerance class in our example is C, means coarse class. If the letter, okay, at the title block it has been shown is M, this means tolerance class is medium. You see the first letters of the words are used. If it is F, this means tolerance class is fine. If it is B, very coarse. Okay. In our example, it is coarse. Okay. And then dimension is 60. Well, the same rule is valid for this table. Well, these are the range values to locate the nominal values. Okay, first number is not included, second number is included. Okay, so if the value were 30, we would select this range. Because 30 is included, that 30 is not included. But in our example, 60 is the nominal value. Nominal value is equal to 60. In answering the questions, write the things clearly on the exam sheet. Let's say 60 is a number. It finds its place in this range because 60 greater than 30, less than 120. Okay, this means need to follow this column. Well, since the tolerance class is coarse, need to follow this row. Okay, follow the row, follow the column, and then meet over here within this pigeon box. And the pigeon box, the written numbers, all the pigeon boxes, written numbers are in millimeter. There is no trick in this table. The deviations in the previous table are in micrometer, but the deviations in the tables within this document are all in millimeter. It is written as it is written. So, well, in our example, upper deviation is equal to plus 0.8. Last few more minutes, dear students. I know it is just the time already, but sorry, I'm going to use one more minute. Okay, upper deviation plus 0.8. Lower deviation is minus 0.8. Okay, under your awareness, writing the unit of measurement, say that it is millimeter. This is millimeter, not micrometer. And then one more step, upper deviation, upper limit, sorry, upper limit is equal to 60 nominal value plus upper deviation 0.8. And this example, this means for the height of the object, upper limit is 60.8 millimeters. Okay, lower limit is equal to 60 plus lower deviation, it is negative, minus 0.8. It is equal to 59.2 millimeters. Tolerance is equal to upper limit minus lower limit. So in our example, tolerance 60.8 minus 59.2 means 1.6 millimeters is the tolerance. Okay. To determine the upper lower limits of external radii and chamfer heights, table is the second table. Okay, to determine the upper lower limits for the angles, for instance, angle, there is a projection of an object, and we'll say we have an angle. Okay, say that it is 30 degrees. Angle has been shown like this, 30. Okay, it is the size of the opening between these two inclined surfaces. Well, here refer to the table 3 for finding upper lower limits for this angle. But here in selecting the range, there is a trick, my dear students. Well, for instance, saying that over 10 up to 50. Lots of students, while studying on the previous table and saying that upper lower limits, consider as if those the upper lower limit for the angle. And say that, yeah, well, since 30 is greater than 10, less than 50, and this means it is the range. No, it is absolutely wrong, because the written numbers are not degree in degree. As it is written over here, the written numbers just corresponds to the shorter side of the angle. Well, for instance, the length of the surface here, the edge of the length of the surface, for instance, 30, or say 40. Okay, the length of the other surface, these two surfaces are inclined and forming an angle between them. Let's say it is 50. Then standard says that consider the length of the shorter edge of the ray, edge of the angle, as nominal size. In our example, the shorter side is this side, so located in the range. 40 is a size, it is in this range, but the range, the boundaries of the range, just length, not angle. Since 40 as the length of the surface is less than the size of the other surface, well, standard says that take that number as the nominal size and then locate it in the correct range. So, well, and then, well, our class is course in our example. So from this column, from this row following, can see that upper lower deviations are 1. So upper limit 31 degrees, lower limit 29 degrees. And the tolerance for this angle in our example, tolerance is equal to 2 degrees. Okay, now finish this chapter, and then the next video report, it is going asynchronous video report, will be about CAD application in AutoCAD in Inventor, how the dimensions are shown. I'm going to answer these questions, okay, in the following 2 video reports. Dear students, well, time to take a screenshot. Do not leave the Zoom session, please. Well, only few students could attend to the class, 8 participants, 8 students, taking the screenshot, and then can say that bye-bye. Yes, now you may stop the session. First, let me stop